Okay, so how you doing? We're going to talk about, very quickly, this equation y equals 1/2 sine of the quantity of x plus pi. I put a plus 0 on here. You're not going to see the plus 0, but I put it on there because I want to relate back to where all of this really comes from. And, you know, where are we coming up with all of these types of ideas? And the thing that I want to explain to you is that I'm going to talk about an exponential function. And I'm going to talk about the most basic exponential function there is. And we're going to start off with this y equals x squared. And we're going to talk about what happens during an exponential function. And the reason I want to talk about why we need to discuss this idea of an exponential function and why is it that this is going to hold the same properties that an exponential function does. And the whole reason for that is because these are exponential functions. Now, they're cyclical exponential functions, and what I mean by that is when I take this ratio and I put it onto the xy plane, it then becomes a function. It is part of a circle. The ratio is gained from a circle, but when I plot that ratio by itself on its own axis, it becomes a function. What I mean by that is that you have this formula for a circle centered at the origin, which is what really we're talking about a lot in trig. And the idea is this x squared plus y squared equals r squared. And what you've learned along the way is that sine of theta, okay, is equal to y over r. Well, if I rearrange this for y over r, I want you to see what type of function y over r that ratio creates. So y over r, so essentially what I need to do is divide everything here by r squared so I can get the y over r. And what you're going to be left with here is that you have this x squared over r squared, okay? So just showing this work, I'm just going to erase and go along as the way. So what you're left with is this x squared over r squared plus y squared over r squared is equivalent to 1. And then I subtract it from both sides, okay? So I subtract the x squared over r squared from this side, and I'm left with y squared over r squared is equal to 1 minus is x squared over r squared. Solving this now for y over r, I'm going to raise this. I'm not going to use the square root. I'm going to use the exponential notation for a square root. So I'm going to say this to the 1/2, okay, which is going to be the same thing as doing a square root. Take this whole quantity to the 1/2, and what I'm left with now is y over r is equivalent to the function of y 1 minus x squared over r squared to the 1/2. And what I now have is that this ratio is equivalent to an exponential function. So why is it that these are going to hold the same properties as the other exponential functions? Is simply because your y over r, that ratio that you're saying is sine, okay, also is an exponential function. So that's why these values are going to hold the things I'm about to talk about. So that's where all of this idea comes from, or why all these things are going to talk about that. Now, talking about y equals x squared, that's my base, that's my parent function. So I draw my parabola in. What I want to talk about is there's a key important parts that we worry about in a parabola or an exponential function. And things we worry about are local max, local mins, inflection points. Essentially an inflection point is where does it change, you know, its curvature or something like that. But what I want to talk about here, right, is this one. I'm going to talk about this point for a little bit, and I'm going to talk about the very next point. So what we have here is that if I have the parent function and I double it, so all I'm going to do is say double the outputs. So whatever I have, I'm going to still do x squared. I'm still going to do x squared first. I'm not going to do anything prior to doing that. Still do the x squared, and then I just double my answer. My origin doesn't move, but my points move up and down. So what I want you to note here is that this point gets farther away from the x-axis, which means it moves up. And that's important because when we get to sine, we're going to talk about how our points go farther up away from our centering axis. So anytime I multiply the function by whatever it is, it directly impacts the outputs by that amount. So what I want you to note is that the output was 1, it's now 2, okay, for this one. Now, for when I go to this one, I'm still doing x squared first. That's the important bit you need to that's the important bit about this. That you still do the x squared, and then you take plus 3. So what I'm doing is that the 3 is an addition to the function. It's not inside the function, it's an addition to the function. So I take my function now, this one, and I make everything 3 more than what it is. So I take the output and I make it 3 more. So the output, if the input was 0, the output was 0. Well, now if the input is 0, the output's 3, because 0 plus 3 is 3, which is why my graph, this whole graph, I pick it up and I just move it up. I just move it up. And the thing I want to talk about is that these points stay snapshot, which means I go over 1, up 1 to get to my next point, and over here I go over 1, up 1. So that's an important thing to understand. So if I have an addition outside of the function, then it moves my graph up or down. This one's important because the addition occurs as a quantity squared. So my addition is actually occurring inside of the function. So I don't actually just have to do x squared. I have to take this idea of x plus this 1 squared. Well, this one's a little bit easier to see because what I've done here essentially is I've come over here and I've input a value. I've expanded this x plus 1 to its polynomial form, which is x squared plus 2x plus 1. So I turn it into a trinomial. And then I plug some values in. So the first one, you go 0. Plug 0 in, you get 1. So now, when I plug 0 in, okay, it's no longer 0, 0. It became 0, 1. All right, so that's important. But the thing that I want to talk about now is the minimum of this curvature. And the minimum of this curvature now occurs at the point -1, 0. When I go from this point to the next point, is it snapshot? And if it's snapshot, then my values aren't being doubled. There's no multiplication going on. But if I take a look at this, I go over 1, up 1. So therefore, it still is kind of relating back to this regular parent function. The only difference is that I've moved it to the left. And what I want to notice here is that this was a positive, and it ended up being a moving to the left. So what you need to remember now is that if it's an addition, you move it left, and if it was a subtraction, you move it to the right. So these properties hold true for all exponential equations. So going back to that idea of this, graphing this, I'm going to apply all of this, okay, all of these properties, to this one problem at one time. So here we go. Let me just erase this very quickly. So remember, if I multiplied the function, that affected my height, okay? A height on a cosine or a sine wave is called the amplitude. So the height of the wave from the x-axis is called the amplitude. Okay, and remember it was a direct impact. So my amplitude now is 1/2, which means my point for this, okay, is the highest point off of my x-axis when I draw this in here, is only ever going to be 1/2 unit away from the axis. So let me go ahead and draw this axis in here so you can see it. So if this is 1 and this is -1, okay, which is the original domain or the original range of my sine curve, my new range goes from positive 1/2, sorry, to -1/2. And that's because I multiplied these values, which originally are 1. I'm multiplying it by 1/2, and 1 times 1/2 is 1/2. So that's why my new values range from 1/2 to -1/2. Now we have this other thing called what's going on. So what's going on inside of this function here? Well, guess what? The original parent function is sine of x. Remember how I talked about if I have an addition inside the original parent function? That makes it have a shift. So it actually moves the graph left or right. And remember how I talked about that if it's positive, for this one, you're going to move it to the left. So what this means is that all I'm going to do, there's an addition inside, so it means I move the function left. Alright? Now, the other thing I didn't talk about was what happens if you have a multiplication inside the function. And the only reason I didn't do it is because for this particular video, if you want a video that talks about what happens if I multiply in here, I'd be glad to put it up. Just for this one, I'm not. So Now the plus 0 here. The reason I showed that is because I wanted to show that my original point for the sine function, okay, started at 0, 0, so I'm not going to shift my point off of this axis. My starting point is still going to be on the zero value for the outputs. So all I now have to do is go over, label my axis now, so I usually wait to do this. And I have x plus pi, so I'm moving it to the left pi, so I'm going to call this pi over 2. I'm going to call this pi. I'm going to call this pi over 2, call that pi. Okay, so negative pi over 2, negative pi. And the reason I'm going to negative pi is because I'm going to talk about this value right here actually shifted my graph to the left. So it shifts to the graph to the left, so it takes this point and moves it over here. So now I have a new starting point at negative pi. I'm not doing any multiplication to the function that's going to make it squeeze in or squeeze out. So there's not going to be any sort of values that are going to make this function squeeze in towards squeeze in, which means basically you can have a stretching of your graph or you can have a shrinking of your graph. My sine curve, if there's a multiplication inside, that occurs the stretching of your graph, okay? Or it makes it shrink. And because in this one there's no multiplication, my graph isn't going to switch at all. So essentially what I'm going to do here is I'm going to draw in the original sine curve. So the original sine curve starts at 0, goes to pi over 2, goes up to 1. Okay? At pi, it comes back down to 0. At 3 pi over 2, so 3 pi over 2, okay, it goes down to negative 1. And then again at 2 pi here, it goes back to 0. So the original function I'm going to dash in here. Right, so there's the original function. So let's just talk about what happens. So essentially, because there's no multiplication on the inside of the function, I don't have to worry about a stretching or shrinking. So I'm just going to take all of these 3 snapshotted points and just move them left. So what that means is that my new points are going to be, if I take a look at these are all pi value away. So they're all going to be a pi unit away. So from here, my newest point is now here. And then my next end value is here. Okay? So that's important. So I've essentially got my new points here. And the last thing I want to talk about here for this one is I've now taken care of my shift. I got to talk about this amplitude. So this amplitude just simply means that for the original function I started and I went half, okay, 1/2 pi, and then I went up 1. Well, in this case my amplitude is now a half as opposed to 1, so I go 1/2 pi to the right and I only go up a half. I go right, I'm back at 0, I go over, I go down 1/2 pi, and then I'm going to draw my new graph in, and I'm going to use a bold line for this one. Okay, and what I got there is my new graph. So I hope that original discussion about the exponential functions helped you understand this a little bit more, but essentially this is what you're doing to these functions, and that's why my points got shrunk down, and the addition inside the function is why I moved it to the left. So I hope that helps.